long, but it's okay. Like a few words, I think that need like more clarification, I guess. But I will spend maybe like 10 to 15 minutes just explaining the framework of like robustness, what we're trying to achieve, just like more general, in a general way, and then I will get more to details into this very specific problem. Okay, so please feel free to stop me whenever you want. If you have any questions, I'd like as much to make it interactive if you guys want to. No, it's not working anymore.
Wicker isn't working.
It was working before. Oh, okay. All right, so let's start with the first things first. Okay, so this is something that you guys are all familiar. This is what you learned like in undergrad, the law of large number. You have this example of IID observations with like some expectations, right? And you know that the law of large number tells you that if you're trying to estimate the mean, then the average or the empirical mean is always like usually a good, consistent, what we say, consistent estimator in the sense that it converges. You know, as n grows, you get very close to the true parameter you're trying to estimate. So this is usually like, this is even true without like existence of like further moments, like second moment or anything. You have actually this like strong law of large number. Now the thing is, this is mostly like from an asymptotic perspective, okay? So we know as n grows, that's what happens. Now, it turns out that well, if you fix n, the sample size, you might want to know like how close we get to this parameter, okay? How close is this estimator, the empirical mean? And obviously, this will depend pretty much in the distribution, okay? While this is a universal result, that does not really depend on the distribution. How close this estimator is how close it is to the true parameter depends pretty much on the distribution. Okay, so pretty much what we care about now is a non-asymptotic version of this. So now if you assume the existence of the variance, if under like two moments assumption, you might be interested in quantifying the error. So you know, like I'm getting so close to mu, that is the expectation, but how close do I get? Like I'm trying to quantify the error I'm making for fixed n. How close is this epsilon, which is like the width of your interval, the confidence interval. And it turns out that for some distribution, this interval is small. If you have usually if you have light tail distributions, you get like a small interval. If you have like heavy tail distribution, it gets larger. And the goal is to try to make, what we want ideally is to have an estimator that has like a small like width for the confidence interval. So basically, I mean, usually that what we teach to our students in undergrad class, when you give an estimator, usually you give a confidence interval. I know that with 99%, like my parameter falls into this interval. And if you can make this interval small, then you know that's basically, as a statistician, that's what you're trying to achieve. So without making any assumption on the distribution under just existence of two moments, it turns out that you can use the basic inequality, that is Chebyshev's inequality, to quantify this epsilon, the width of this interval. And it turns out that if you make no assumptions, it would scale. So basically your interval would scale as 1 over delta. So if delta is your like confidence level, that could be, that's usually like very small. Like if it's 1%, it's really small. Then the width of the interval would like scale like inversely proportional to delta. And the dependence in delta is quite bad. It's like 1 over delta. And we know pretty well that for sub-Gaussian observations, think of the Gaussian case. This actually, we can show that this epsilon, thanks to concentration, scales as log 1 over delta. So basically, you get a much better dependence in delta for like when the lights are light compared to like heavy tail. Okay. It turns out actually under just 2 moments assumption, you cannot improve. You cannot do better than this for the empirical. So while we know that it's consistent, it turns out that the empirical mean is not always a good estimator for like finite sample as n is fixed. Okay, so that's why there's been a lot of work trying to improve, to come up with new estimators that are not the empirical mean, that could probably reach something similar to the sub-Gaussian. So usually what we call the sub-Gaussian deviations are estimators that would give us something that looks like a Gaussian confidence interval, even if the data is not necessarily Gaussian. Okay. So in general, achieving sub-Gaussian deviation is exactly this, trying to get those like sub-Gaussian confidence intervals under like general assumption of the distribution. Okay, So again, we know that asymptotically under like two moments, the CLT tells you that actually as n grows, you can actually achieve this. Because you know that your empirical mean would have this like a universal behavior that would behave as a, if you renormalize it properly, it behaves as a Gaussian. So we know that asymptotically this, this is actually true. You get this very small, very tiny like confidence interval. And now the whole point is, can we prove something similar for fixed n? Like, can we give a non-asymptotic version of this? Can we fix n and come up now with an estimator that is certainly not the empirical mean, that under just two moments can achieve this, can have like a similar one. Yeah.
A silly question just to make sure. So this twice under the square root, it's because in the Gaussian density you divide over twice sigma square, right? So like to make it really Gaussian. This is the reason why.
No, the two that's in the Gaussian distribution is this one.
Yes.
I'm assuming this is just for the absolute value.
No, this I understand. Yeah, this is so that you can treat the case delta equals 1. But like this is twice the locus because it's twice sigma squared. Right?
This two or this?
No, the first one.
This two? Yeah. This is because you have like we divide by 2 in the distribution. Yeah. It's like t squared over 2. Okay. All right, so that's basically what we're trying to achieve here. And it turns out there is a lot of work actually like about like estimators in this area. Actually, like a lot of robust procedures. Probably the most like the most popular ones are going to be the trimmed mean, which is like a simple estimator where you just take your data and you try to throw up like whatever the 10% like largest or like smallest or like 5%, largest or smallest like observations, and then you just average out whatever is left. It turns out that that's a very good like estimator in terms of what I will explain later. Another procedure is called the median of means, where you basically, in general, the median turns out to be a more like a robust estimator compared to the average. So basically what you do there is like you split your data into buckets, you compute averages within each bucket, and then you take the median of all these averages. And that's what we call the median of mean. And these two estimators turned out to be like pretty good, okay, for like fixed n. And then with stats, actually, we worked on a different approach last year, which is like it's based on like self-normalized sums, which is a pretty intuitive approach actually to construct another robust estimator that's actually improving these two, where it's also like it's also efficient in the sense that it has the right variance corresponding to what you would have in the Gaussian case. So these are just examples of that we know how to do things in general, like under this simple model where we're just trying to estimate the mean in dimension 1, everything is well understood. Something that I want to point here before we go further is that in general, for all these procedures, we need to fix the confidence level. So K is usually, for the trimmed mean, K is going to be proportional to the number of the fraction that we want to throw away. That's going to be represented by K. For the median of mean, it's going to be the number of buckets that we'll use. And usually this parameter that we need to tune for our estimator depends on the confidence level. So in other words, you have to specify your confidence level you're trying to reach, okay? You just say, I want to have this interval with probability like 99% or 95%. And once you specify this level, you can construct your procedure that would achieve exactly this confidence level. Meaning that if you change now your confidence level, you will probably have to compute your procedure again. So it's unlike the Gaussian case where you have where the average empirical mean is sub-Gaussian for any value of delta. This is now different because because the distribution is not as nice as Gaussian. It only works for one specific confidence level that you need to choose before in advance. Okay, so you give me your confidence level you're trying to target, and then I can construct an estimator that achieves, okay, this like sub-Gaussian deviation corresponding to this exact confidence level. And again, it turns out under just 2 moments, we cannot construct estimators that would work for all confidence level. Actually, it turns out that it only works for.
Interesting. What about Levsky's adaptation?
For what?
Like, let's say you have a family of this median of means, right? And you choose like in this case, a number of buckets, right? So can you just feed it to the Levsky procedure that would kind of select the right one based on the data?
But what you're talking about is for the number of outliers. No?
I mean, for anything, right? Because if your family is ordered, which it is here, you can just apply it. The question is the logs. I mean,
it was done by a paper by Lugosi, Oliveira, and Roy, 2016 paper. They they do it, the problem is for Lebesgue's method, you need to know the variance.
Ah,
If you want to
okay.
construct it.
Yeah, I see. Okay.
But yeah, you can do something like that basically.
No, I know, I read, I know.
But you have also the counter examples where you cannot, like you can show that under just 2 moments, you can only construct for a given confidence level, like an estimator that would not work if you change your confidence level. But there have actually like a.
I mean, if you don't know the variance, that means you have to be adaptive to 2 parameters. And the classical Lebesgue's method will not work because it requires ordered family, right?
Yeah.
But that's kind of might be the reason.
Yeah,
We can discuss offline. It's a good question.
I honestly don't. Okay. Well, we can talk about it later. But I
Yeah.
really don't think it's only because of that adaptation to sigma that you don't have. But anyway, for now, what I want to point out here is you have to fix your confidence there. Under just 2 moments, you cannot hope to do like better, like to have like a full range like of confidence interval. So it's just like for this specific choice or this specific confidence level, that's what you can get. So this is just to achieve those like small confidence intervals, but it turns out that these estimators are also robust under what we call adversarial contamination that I will explain in the next slide. So adversarial contamination means that within your n sample, you can allow an adversary to modify O data. So you take a fraction, let's say, O points among n, and you'll allow an adversary to just change them however he wishes. Okay, and this is what we call the adversarial contamination. And it turns out that the same estimators that I showed you before, these like trimmed mean and median of means, if you choose again k, now that should depend on both the confidence level and the number of outliers, then you can show the following bound. So this is the sub-Gaussian deviation, and this is the price you have to pay for corruption. Because you have these outliers now that really like make your estimator bad. And it turns out that this is optimal. This is basically the best one can hope for. And the 2 estimators, median of mean, even the one the self-normalized one that we proposed with stats, they all like satisfy this basically, this bound. This is minimax optimum. This is that you cannot improve this. It turns out that for sub-Gaussian distribution, you can improve this square root here over n to like a real O over n. If it's Gaussian, it's exactly over n. If it's sub-Gaussian, you still have to pay for this log term. But it turns out that from 2 moments to sub-Gaussian, if you have like 4 moments or like 6 moments, you can improve this, and it's kind of interpolates from square root to over n. So there is like a full interpolation depending on the tail of your distribution. So this is good, but again, I wanted to remember here that this k always should depend on the number of outliers and the confidence level. So it's not completely adaptive in the sense that you need to know O in advance. But again, you can do something like Lebesgue, like you said, if you want to be adaptive with respect to O. Usually you can make things work. But if you just want to construct just the basic method without like Lebesgue adaptation, you have to know these 2 things in advance, basically. Which is not practical, right? We don't know the number of outliers in advance. That does not seem like a practical thing.
Or you can probably say that you can replace this requirement by requiring that the distribution is symmetric, for example.
If your distribution is symmetric, then yeah, you can do better than this, yes, for sure. But it's I always think it's cheating when you say it's I think it's symmetric, but yeah, well. Is it enough that just symmetric? Because you can always take the differences, but then you subtract the mean, you cancel the average. Yeah, okay. So things you can do better if the distribution is symmetric because you don't have this bias issue that we usually struggle with. But anyway, so this is what you can achieve, and we know that problem solved. Like for just the mean estimation, this is the best you can do, and we know that we have methods that achieve this. Very good. So now, this is like a long slide. This is now the problem we will care about. So this is what we care. This is the simplest model you can consider, which is like the linear regression model. Forget about this term for now. You just observe like a linear model plus noise, okay? And then you have to think of this theta star as a very sparse vector, meaning that theta star only has like few of the coordinates of theta star non-zero. This is the adversary in some sense. You can think of theta star as some adversary that would take your n observations and just like modify maybe O entries of among your n. So theta star only has O coordinate different from 0. So we don't know what theta star is. That's the adversary that just can change any of your entries. And beta, that is our linear, the coefficient, the signal we're trying to estimate is also sparse. So in general, like in statistics, for many problems, it's very relevant to make this assumption, especially in high dimension, that the signal you're trying to estimate is sparse. So this is just a sparse linear model where we allow an adversary to corrupt our observation sets.
So the adversary knows before the observation kind of knows.
He knows everything.
Yeah.
Yeah.
The noise is added not after, but before the adversary. The Gaussian.
The theta star can depend on psi, can depend on x, can depend on anything. Yeah, it's really like the very general like adversarial contamination. And what we will assume here is that our noise here, rather than assuming the general assumption that it's sub-Gaussian or Gaussian, we will assume that the tails of the noise actually like depend on some parameter tau. So it's like a decay of the tail 1 over t to some power tau. So if tau is equal to 2, that's well will correspond to just like the Cauchy distribution. And then as tau grows, you know, for like just an abuse of notation, tau infinity would correspond to the sub-Gaussian case. We just assume that this is like a very nice distribution and would correspond to exactly this deviation. So the noise is not exactly, we assume that we know the class of distribution where the noise belongs to, but we don't know exactly what distribution it is. It just belongs to this class that has these deviations. We're not making a lot of assumptions here. We only want okay, well, maybe this is a little bit of a strong assumption. We want X, I will tell you later why. X is supposed to be a sub-Gaussian design, meaning that you know, the rows of X are sampled, are IID, and like each row has this exact covariance sigma that we don't know necessarily. Okay, we don't assume anything about the condition number of sigma or like the spectrum, anything. We just, you know, we can always renormalize sigma so that all the diagonal terms are like smaller than 1. And other than this, we don't assume that we know sigma in advance. So it's just a random design that we're working with, but we don't assume exactly that we know the distribution of the underlying distribution of this design. So we still, like, even if it's a simple model, we try to leave it like a little bit like general without assuming too much. And we'll see what we can do with all this assumption that I made here. Are we okay with the model? Okay. So so the goal obviously here is to estimate beta star. So you could think of estimating both beta star and theta star, obviously, because they're like both parameters here that are unknown. But what we care about, this is just a nuisance parameter for us. What we care about is the signal. Okay, not necessarily the contamination. Okay. So actually there is a huge literature around this problem, the just linear regression under like heavy tail or like corruption. And I remember like Sam Hopkins, when he visited like was it a year, like 2 years ago, he exactly talked about this. And actually they considered the same problem with unknown covariance. And their goal, without like corruption, without like outliers. So remember that when I say robustness, it's both either for sub-Gaussian deviations or corruption with outliers. They only considered the case with heavy tail.
Panjeri, right, the first step.
Okay. I think that was with them, it was this group. So basically they showed that without the sparsity assumption that you can reach this error P over N, which is optimal, plus the sub-Gaussian deviation. You know, so they can estimate beta star under heavy-tailed noise, and also like heavy-tailed like regression design. But the problem is they required N to be like of order, if you want to have the optimal dependence, N could be of order P squared, or like P to the power 3/2. That was the main problem they struggled with. While N of order P is exactly the necessary, and it should be sufficient to require N of order P basically. And they have this method that requires more than 10 moments. It's a very technical paper, but at least they were, I think, the first to have like a polynomial time method to achieve this, even if it's not fully optimal, but at least they come up with something that's structurable. But it's not optimal in the sense that they have to estimate sigma in advance. This step of estimation of the covariance is what makes it like what costs them this price, basically. So that's one of the attempts, but in a similar problem that I started actually looking at before we started looking at this problem, a similar model is exactly this, where now we assume that theta star is independent. Okay, so it's not like fully, it's not an adversary, because in the sense that you can only add some contamination that's independent from all the rest. And they also assumed in this paper by Bahati and co-authors, they assumed that the noise is Gaussian, I think. So Gaussian noise and this oblivious corruption where theta is independent from all the rest. And the only good, the surprising result here in this paper is that you can achieve an estimation error that does not depend on the fraction of outliers. That was the most surprising, in the sense that if n goes to infinity, you have a consistent estimator. While usually in robustness, you have to pay always the price of O over n, the fraction of outliers, you still need to pay this price. It turns out that under this model, the oblivious corruption, you can have a fully consistent estimator where basically the fraction of outliers does not appear in your bound, which is just a surprising fact. But again, is this model really realistic? It's probably not it's too simple for a model to capture exactly what's going on there. But they were the first, probably, I don't think if they were the first, but at least they tried something to use this optimization problem. So rather than estimating beta alone, so the idea here is to think of beta and theta as a bigger vector, just concatenating these two vectors and thinking of this regression. So if you think of, when you write y is equal to x beta plus theta, you can always think of it this way as some bigger regression problem. Okay, where it's x beta plus theta. Okay, and now what you're trying to do is you're trying to estimate this full vector, basically, and you only keep the p first coordinates. You can always think of this exactly what you're trying to do as a bigger regression, a regression problem in a bigger dimension, and where you only care about the sub vector of the whole vector.
Actually, might not be that surprising because they consider the case when sample size is larger than the dimension, right?
Yeah, that's true.
So in this case, you are essentially estimating subset of coordinates in usual regression. So it's not that surprising that it only depends on the number of coordinates you want to estimate. If your matrix is well conditioned.
Okay.
So
then why is it when theta depends on the rest, why is it that we have to pay the price of O over n? If I just have having a hard time to see why just the fact that theta is independent from all the rest makes you get this bound that's independent from the fraction of outliers.
Well, it's a good question.
I really don't. I try to understand, to find any intuition behind, but they certainly need n to be larger than p for sure. And it helps certainly in the proof, but it's still, in my opinion, it's still a surprising result to see that even if this corruption is very mild, it's not as bad as when a real adversary observes everything and try to mess with your data. It's still, I don't see why, it's this still, but I agree that this is a very simple setup where probably things work better. But what I want to focus here on is basically the optimization method they used. Is think of this regression problem. Now they're trying to estimate exactly beta and theta. And what they're doing is what we do in lasso in general in high dimension regression. You have a sparse vector you're trying to estimate, you penalize with the L1. So here they know that this theta is sparse. So I'm gonna penalize theta because only few of the coordinates of theta are different from 0. It makes a lot of sense to just say, hey, I'm gonna solve this linear regression, this linear regression optimization problem and penalize my theta with the L1 norm. So that what it returns is a vector beta and the sparse estimate of theta, okay?
Okay, so I think I understood what you said, right? So it's so you can estimate the support, right? Because it's kind of a sparse regression, so you can estimate the support. But estimating the support right here, it means knowing where theta is and where it is not. So then you just don't look where it is. Right?
But we don't know where theta is.
Right, but don't they also kind of, as a consequence with this method, don't they also estimate
what messes things up here is, if you had a good estimator of beta, you could know what the support of theta is. But what you're trying to do is to estimate beta, actually. So it's very hard actually to estimate. Actually, what we can actually show, I don't know if this makes sense, but you can actually estimate beta to a good precision without knowing this, without even being able to recover the support of theta.
Oh yeah, that's the main question.
You can.
If this is the case, then it's really surprising.
That's exactly what's going on there. Yeah. So actually the whole thing, we can actually show at the end, we get optimal bounds for beta without the estimate of theta being optimal, actually, in some sense. So you don't really need to estimate, to have a good estimation for theta to.
You're saying because theta is sparse, penalizing according to the L1 norm of theta is a natural thing to do.
Yeah, that's usually what we do in high dimensional regression.
Rather than like.
Sorry? It's usually, actually this thing is, okay, but what's more natural, I mean, for people who are not familiar with this, what's more natural is to penalize with the L0 norm. That's more natural. So you're trying to come up with something that would minimize this thing. So it would return an estimator that would have the smallest number of coordinates, right? The problem is this is not like a convex problem to solve. And it turns out that the closest thing you can get in terms of convexity, in terms of norms, is the L1. Actually, like as you increase like this, if they're not exactly norms because they're like concave, but as you reach the L1, that's the best, that closest you can get to convexity, and that's what works in practice. Yeah. So, again, we're trying here to come up with something practical. We're not just trying to find an estimate, we're trying to find something practical. So this works pretty well, and this is very simple. Remember, our model is more general. This is not enough, actually. This alone is not enough for what we're trying to do. Okay, so as for the lower bounds under our model, actually we figured, okay, so there is this paper where they have this lower bound, but we had to do it again with stats because this lower bound were like not exactly our setup, but it's something similar. So it turns out that the right dependence under adversarial contamination is over n to this power that depends on the tail. Okay, so 2 minus 2 over tau. As tau goes to infinity, which is the sub-Gaussian case, you recover the squared over n. When tau is equal to 2, you recover exactly over n, not the square. And it actually interpolates between the two as tau like changes from 2 to infinity, basically. In that paper, again, they have a polynomial method that's not exactly optimal because it requires like a bad dependence on the sample size to achieve this bound, basically. So remember, if you don't have the sparse assumption on beta, you have to pay P over N for the estimation error. Obviously, now that beta is also sparse, we can do better than P over N. We can get like something smaller, but the dependence on outliers does not depend on how sparse is beta. It only depends on the sparsity of theta. So this is always a lower bound, no matter how sparse is beta. Okay, remember, this is exactly what we were trying now to achieve or to reach as when we construct a procedure, we want to get like this as an upper bound. All right, so then the most recently paper by, I don't know, the first one, Pollinglow and co-authors. So they consider the exact same setup, again, without sparsity for beta, but now they're assuming that the design is isotropic, heavy-tailed, so it's like a more general setup than what we consider because they consider like heavy-tailed design with probably some corrupted covariates. And actually they achieve this like the optimal bound. That is exactly P over N, the log for like the sub-Gaussian deviations, plus the right dependence on O over N. So this is an optimal result with a nearly optimal condition N over P roughly. So this is the best you could get so far. The only problem is they require this first step that's basically to clean their design, which is this like black box instance using some of Diaconicola's like algorithms where they just say, okay, if we assume that we can clean the covariance using this black box method, then now we have a design that is clean and we can do all of this, okay? Again, so it basically rather than saying we have a sub-Gaussian design, you can always say, I have this design that if I clean, I get back to like almost sub-Gaussian. So it's cheated. Again, in my opinion, when you say stuff like that, it's not very, but it's better to sell a paper, I think, to say that we don't consider the more general case. But anyway, this is how it looks, the kind of results we're trying to reach. This is optimal in terms of the statistical accuracy, sub-Gaussian deviation, and the dependence on outliers. Okay, so what we're trying to do is trying to reach something similar to this under sparsity of beta, which I will talk about in a second. I don't know if there is something else. So, okay, all these methods that I showed you, like this Hopkins or Pollinglow co-authors, they use like some very, very like complicated methods usually to come up with these like robust methods. What we're trying here is like to come up with something. Can we do something very basic, very simple that can still what? It's actually the question like that we asked ourselves was like quite different. Can we just use like something pretty basic and still achieve something that could be optimal, okay? And actually there was recently, Doubly and Thompson had this very nice paper that when we first talked about it with Stai, it was quite surprising because they considered the same problem where you have, you have this adversarial contamination and sparse signal, okay? And now what they decided to do is we're gonna penalize both beta and theta because we know that beta is sparse, theta is sparse, let's just penalize both and just solve this simple linear regression optimization problem, okay? So this is a doubly penalized estimator where I'm gonna penalize both. It's very natural to do this, we're just solving a linear regression problem and then penalizing both parameters, okay? And it turns out, actually, the surprising result was that this very simple method that initially, maybe like 3 years ago, you would ask someone, would tell you for sure that this cannot be optimal in terms of, for like robust guarantees. But it turns out that if your design is sub-Gaussian, then that's what they assume in the paper. If the design is sub-Gaussian, not corrupted, if your design is clean in some sense, which is also what we assume in this work, then you can reach this bound for like Gaussian nodes or like sub-Gaussian nodes. So they only assume that the nodes is well behaved. So this dependence S over N, sparsity over N is the optimal dependence. And over N, again, if you square this error here, this is over N squared, which is exactly the optimal dependence on the fraction of outliers if the noise is Gaussian, okay? So it turns out that this simple method,
logs.
Yeah, it's up to logs, up to logarithmic factors. So it's not fully optimal, but it's already very good. To think of this very simple program that we can run like a very easy like convex problem to solve can lead to optimal result, even under the probably the strong assumption that the design is sub-Gaussian. But it was still surprising. I don't know for you, but I thought it was surprising at first, like to think that this would be optimal.
What about couple of S?
Okay, this is the condition number that's usually required for for sparse linear regression when you do lasso. This is the condition number, and it turns out it's there are no information theoretical lower bound that show that this is necessary.
No, I just didn't know what it is. It's not surprising to me. If you need to explain to others, then yeah.
Yeah, but actually, my point here is that this is not required. You can think of it in general. It's like a constant. We don't have like a lower bound that this is necessary, but it turns out there are like some evidence that for like computational time methods, especially those like the L1 penalized method, you have to pay this price. But there is no like information theoretical lower bound.
That's that for L0 penalty, it's not necessary.
It's not necessary. If you do L0, you would not need this kappa. So
conditions you don't need them.
I feel like it's hard to argue there, but it seems that for all the methods that we know, at least that are like polynomial time, they have to, at least those, where you do the L1 penalty, you have to pay this price.
From the work of Pierre Belek, does he have lower bound for lasso?
That's for lasso. But I think there is the paper, like an old paper, like a cool paper by Jordan and some like Berkeley people, where they show that even for polynomial time method, actually you need this. I've never really managed to like parse this paper, but they have some evidence. I don't know how rigorous it is, but some evidence that any polynomial time method would, for sparse regression, would have to pay for this this condition number price. But okay, so this paper actually, so it's a nice result. So just to say a few words about those like the penalty parameters, lambda S is for beta, lambda O is for theta. Okay, so lambda S is of order log P over S, and lambda O is of order log N over O. Okay, and they both scale as the variance parameter, the standard deviation, which means that, okay, so the way they say that they're adaptive to sparsity and to the number of outliers is that basically what they do is they replace S by 1 and O by 1, basically. So whatever price they're paying is some log on top of whatever is the optimal bound. So what they say here, we can be adaptive to these two parameters as long as you allow us to pay for like some log terms on top of the optimal bound. So which works pretty well under like sub-Gaussian noise, but the problem is they're not adaptive to the scale level. So they still need to know the scale level, the standard deviation of the noise in advance to build their estimator method. Okay. So this is okay. So far, when we're thinking about it, this is good. But the two issues we thought of with Stas were that the first one is that it's not fully adaptive because you need to know actually the scale level, and like, so we're trying to come up with something very practical here. Okay, so you need, assuming that sigma in advance is not necessarily something you want to assume. And the other thing is, it turns out that all of this works pretty well when sigma is sub-Gaussian, but the moment sigma is no longer sub-Gaussian, this lambda O here would have no longer a logarithmic dependence on O, but a polynomial dependence. And then not knowing O would come up with a bigger price than just a logarithmic factor. So it would no longer be adaptive to the number of outliers neither. So these are the two issues. We're like, okay, this works pretty well in practice, but it's not really an adaptive procedure in the sense that we need to know all these parameters in advance. That's the whole point from pivotal estimation, is that you're trying to come up with an estimator such that the distribution does not depend on any of the parameters. You want to come up with something with a method that does not require the knowledge of any of the parameters, and trying to do basically what these people have done in a fully adaptive way. If possible, if we can like come up with the same kind of result, but being very completely adaptive. So what we came up with is actually very simple. So as a statistician, you know that we have like three issues. The first one was we want to be adaptive to sigma, we want to be adaptive to the two other parameters S and O, and then we want to be robust. So three things. So and all these three things have been looked in the literature but separately. So if you think about like the way to be adaptive to sigma is what we call the square root lasso, is when you consider here the minimizing not the quadratic loss but the square, the quadratic, meaning that just the norm. Usually by doing this, you don't need to scale the penalty with sigma anymore. It turns out this is what we call the squared law. It turns out that this is already adaptive to sigma. That's the way to be adaptive to sigma, is by simply changing the objective function. The other thing is in the literature, again, what we call the slope estimator replaces the L1 penalty by something that we call the sorted penalty, where rather than penalizing all the entries with the same level, we're going to sort them and penalize each one at a different level. So the larger values would be penalized with a different threshold compared to the smallest values. And that's what we call the slope estimator. So again, this is like a different piece of a different ingredient that you can use. And then finally, to be robust, we know that again we can just add minimize over beta and theta and penalize with respect to theta. Okay, so all of these things, all of these ingredients exist in the literature. We just needed to put all of them together. And if you know all of these things, you may think that this would work. This estimate actually is supposed to work because it has all the ingredients to work, basically. So whatever is left, even if it seems easy to say it this way, it was still challenging to show that this estimator is actually like optimal and does similar to what the previous one was doing. And it has the advantage to be like fully adaptive, because here you don't require knowledge of S, not knowing like O, and not knowing sigma as well, because we minimize over the square root of the quadratic loss.
You can compute projections onto this as onto the norm balls for this norms efficiently, right?
What do you mean? If you want to solve this?
When you want to compute it, you have to have such like a composite method, right? Where you would essentially project on the norms of this ball, on the balls of these norms. And you can do this, right?
It was not just a thresholding method, actually. Like an iterative procedure where you just threshold. It's not exactly what you would think, but it's something that you can run actually in practice. It's not it's not exactly what the equivalent of ISTA, where you just you do this, you project, you compute the gradient, and then you threshold one by one.
No,
I think it's a little bit more complicated than that, but it's still something that you can project. I don't know exactly what the projection would be here, but as far as I'm concerned, I know that this is something you can compute efficiently. Yeah.
How are you choosing the gamma Ds here?
Yeah, very good question. Actually, that's what I will talk about in just the next slide. So it turns out that, okay, so the short answer is, so usually how we choose this lambda in linear regression, okay, usually we choose it of this order, like log P divided by N. And the only reason why, so think of lambda as a threshold where you want to filter out the noise. Okay, so what you're trying to do, you want to filter out all the noise variables. Think of the maximum of these noise variables. If they're sub-Gaussian, their maximum would behave as a log P term, right? The max of like sub-Gaussian variables would be over the log p. So as long as you set a threshold of order squared log p, basically most of your noise variables are going to fall behind this threshold. Okay. Now that we're thresholding with respect to the order statistics, we have to think of what are the lambda, the gamma i's are going to correspond to the quantiles of your variables. So you want to see what is the behavior of the maximum, the second largest variable, the third largest one. And this is exactly what the gamma I is going to correspond to the quantiles actually of either sub-Gaussian or it depends on the tail behavior. That's why we need to know the tail behavior, because that's exactly how you choose the gamma i's.
Okay, so the idea is you put your first your like lambda 1 is sort of
the max.
There should be some probability that the max is higher than that,
Right.
some small probability that the max.
Right. So some threshold such that the maximum would have with very small probability the maximum can like beat this, like be above this threshold. So in some sense, yes, you need to know, but the only thing that you need to know about this is the tail behavior. If you give me now the tail behavior of the noise variables, then I can choose, accordingly these gamma i's. This is the only intuition behind the choice of how we choose these gamma i's. So it turns out for lambda I, this is exactly the choice. This log p over I it turns out that this is exactly the level of the ith order statistic of sub-Gaussian variables. So that's why exactly we choose lambda I. So remember that lambda I is for beta, is the thresholding sequence for beta, and mu is going to be the thresholding sequence for theta. So lambda I is, you know that the noise basically, this z variable, which is x transpose psi, behave as a sub-Gaussian because we can leverage the sub-Gaussianity of x so that this whole thing behaves now as sub-Gaussian roughly. So we know that for lambda i's, we only need a sub-Gaussian like level of thresholding. But the problem is for the mu i's, the way to go with the mu i's, you can always think of now that your xi i's are not necessarily sub-Gaussian, you can always divide them into two buckets. Like one bucket where you are bounded by R, and whatever is above this level R, you can think of it as some outlier. So even within your like noise variables, you can think of the largest ones that are above a certain threshold, you can think of them as outliers. Okay? And actually it turns out that if you choose wisely your level R, the threshold, this is like some, it's not a real barrier. It's like R, you choose your R, you specify your R that you want. And actually we can prove something similar to this. So basically, if I specify R corresponding to this threshold, everything happens as if my noise is bounded by R, and the other noise, the noise variables that are now above R, like larger than R, would be as much as like 3 times the number of outliers. So I'm inflating a little bit the number of outliers by a bit, but I can assume that my variables are bounded. Yeah. Oh, 5 minutes. Okay. Well. So actually, this is how you deal with like heavy-tailed variables, is always by assuming that now it's almost as if everything is bounded, and it's as if I'm only paying 2 or 3 times the number of outlier price. So it's actually, this is like a nice trick to deal with heavy-tailed random heavy-tailed noise. So again, this is the level of truncation because they're not like sub-Gaussian variables. Now we know that the noise has some decay like tau, and these are exactly the quantiles actually of corresponding to this tail deviation. So if you choose mu I corresponding exactly to this, so we have like 2 estimators. The first one that is fully adaptive, where mu I depends on I here. Okay, so this is what we call the beta sorted, where we use the sorted thresholding for theta. And then we have a second estimator where we need like the fixed confidence level. So you choose your confidence level delta, and then this is exactly your mu I, which is like a fixed thresholding for all the coordinates. So we have these 2 estimators. This one is fully is sorted. It does not depend on anything. Does not depend on confidence level or anything. The fixed one depends on the confidence level. So they're like 2 possible estimators you can construct here, and they both have different like behaviors. Okay, so these are the properties I feel like I need to show you the results. These are the only properties we need for our design, and that's exactly why we needed sub-Gaussian design. These are results you can show using empirical process theory. They require a little bit of work, but again, those are basically the main results we need. If you can grant these 2 properties, then we don't need sub-Gaussian design anymore. So the only reason why we need sub-Gaussian is because we know these 2 properties will hold with high probability. Finally, this is the usual condition you assume for lasso to work. You just need your sigma to satisfy this, but I'm not going to spend time on this. But let me just show you the result. The first one for the fixed, remember the fixed level, the fixed confidence level, we can show that the quadratic, the square loss now is smaller than S log P, which is the optimal deviation. It has sub-Gaussian deviation log 1 over delta divided by N. And then you have also the optimal dependence on over N, except that we have to pay this price now, O over log 1 over the delta. So what happens here is, as long as the confidence level is larger than O, this term is basically a constant. Okay, so if you tell me, if you give me in advance like the number of outliers, if you tell me like, and like I specify like a confidence level that's larger than O, then whatever I get is optimal. This is the optimal thing you can hope for. And remember what I told you earlier about the median of mean or the trimmed mean, they all require this condition that K should be larger than O, which is exactly also something that we need here. It turns out that we can make things work, like probably using Lipsky method on top of this. I'm sure we can. But just for this, the estimator, the way it is, it would require log 1 over delta to be larger than O to be fully optimal. Okay. So you get, again, so meaning that actually we improve what Doubly and Thompson did. We have now this fully adaptive method that works also for like any type of noise, not simply like sub-Gaussian, that is optimal and that also has like sub-Gaussian deviation. So in some sense, it really generalizes what they've done in a fully adaptive way. So that's for the fixed level one. The other one that I find quite interesting is the one where you don't fix. Remember that the fixed one depended on the confidence level. The other one, the sorted one, does not depend on the confidence level. It's a sorted penalization method. And it turns out that the other one, for any confidence level, you get now this. That's not just for one specific delta. It's like more general for any delta. The problem is the dependence on the corruption is no longer optimal, because now rather than having 2 minus 2 over tau, we have 2 minus 4 divided by tau. So it's suboptimal in terms of the dependence of the fraction of outliers, but it's something that works for any delta. It's like it's a pretty intriguing like result here, that behavior. But if you think of the special case now, if there is no outlier, if there are no outliers, if you think of O equal to 0 now, if you only have like heavy-tailed data, it turns out that under tau larger than 4, if you have 4 moments or more, you actually recover like full sub-Gaussian behavior, as if everything is sub-Gaussian. Even if the noise is not necessarily like sub-Gaussian, but it's very interesting. But the thing is, the way the proof works is like you leverage the fact that the design is sub-Gaussian itself, and the fact that the design is sub-Gaussian helps you recover this like some sort of like this sub-Gaussian like. So remember, under just 4 moments, you get this full sub-Gaussian behavior. It's not even like a fixed level. For any delta, you get something that behaves like a fully sub-Gaussian like estimator, which I think is a pretty nice like feature to have here. Again, it uses heavily the fact that design is sub-Gaussian, but it's still not something that I've not seen like a similar behavior in robust literature. The other one is if tau is infinite for the sub-Gaussian case, you recover exactly what Doubly and Thompson had, which is the optimal dependence even in, because remember the problem here was that the factor 4 instead of 2, but as tau goes to infinity, this just disappears now. So you're still optimal for sub-Gaussian. We recover what Doubly and Thompson did, but now we have a full sub-Gaussian behavior. Like this is true for any delta. It's not even for a fixed. Which probably is more intuitive here, because if your noise is sub-Gaussian, if your design is sub-Gaussian, you probably expect a full sub-Gaussian behavior. This is probably, in my opinion, more less intuitive, let's say. Okay, that's pretty much. So there are like mostly, I think the real interest I think in this work was that to leverage nice feature of the design in order to get like an improved results for your estimation problem. We could certainly do this like for under like less than 2 moments, like without existing variance. We can still, I think, improve, show similar results. But it would be very interesting, I think, to do the same thing now if your design is not sub-Gaussian. That would be the hard thing to do, is like, what if your design is heavy-tailed and it's probably even corrupted? Can we still like show like similar result? That would be really interesting to do. And I'll just stop here.